So for this, looks like they have two forces. Does it look like those forces are balanced?
Yeah.
So it looks like for the 120 gram mass, there is a weight force that's on the mass from the Earth, and looks like there's a tension force on the mass from the, what do you guys call that, string or rope? Okay. Any questions? Okay, give me a hand. Nice. Number two, then, it looks like, again, they have two forces, and it looks like they're balanced. There is a tension force that's upward on the mass from, do you call it rope or string? Rope. And there's a downward weight force on the mass from the Earth on the 200 gram mass. Now, you didn't have to draw both of them side by side, but if you were comparing this free body to the last free body, how does the weight force in this one compare to the weight force in the last one? It's longer?
Yeah.
Okay. All right, give me a hand. Nice. Look up here for a second. We've got these two free bodies, and you said to draw this one longer. So now what I want you to do in number 3 is basically what I'd like you to do is draw this ruler just by itself. And I'd like you to draw on the ruler, right where the forces are acting, I would like you to draw all the forces on it. Okay? So let me help you with the first one. Actually, you guys help me. Starting over on the left end of this thing, is there any forces acting on it? Yeah, where at? At the 10 centimeter mark. Where is it? Is it acting upward or downward? Downward. And how long should I draw it? Compared to my other free body, how long?
The same length as the other one.
Same length as the
No.
Same length as her? Okay, shorter than that one, but
Shouldn't you make it the same as the free body diagram for the 120 weight?
what do you think about
Mass thing?
what do you think about that? What kind of force is this, first of all? Is it a weight force? So there's a weight force acting at the 90 or 10. There's a weight force acting here?
Tension.
There's a tension, right? There's a rope attached to it. There's a tension force, and that's downward. That's a tension force on the meter stick from the rope. How does the tension anywhere in that rope, assuming it's massless, how does the tension anywhere in that rope compare to any other location in the rope?
It's the same.
It's the same, right? So how does this tension here, the tension on the stick from the rope, how does that compare to the tension on the mass from the rope? It's the same, right? So in a way, it's kind of like the weight right there, but it's not really the weight, right? It's really the tension force that's acting on it. Okay.
Would
So-
it be the tension on the stick from the rope or from the mass? Because isn't,
Well, it's always feeler dealer. What's feeling it? The meter stick,
Yeah.
and then what's dealing it? It's the rope.
okay, you wouldn't consider.
Now, ultimately, what causes that tension is the fact that these two have to be equal, right? But really, what's dealing out that force is really the rope here. So now
Okay.
you wouldn't say the mass.
Okay.
Let's go over on the right-hand side. Maybe we'll just do the free body together, maybe, but don't erase it afterwards. Is there any forces over here on the right-hand side?
Yeah.
Where at? At the 90? Upward or downward? Downward, how long?
As long as the tension force in the previous one.
So the same as this tension force? Okay. So this would be the tension on the stick from rope 2. Okay, any other forces? Sir? There's a normal force, and where at? Yeah, right here at the fulcrum. There's a support force. There's a normal force. How big would it be? Yeah, or
5 plus the force of gravity acting on the ruler.
Okay, now this is a very special ruler. It says that it's massless. You know, sometimes in physics we say it's frictionless because it's a little too hard. We try to do it in baby steps. We start off easy. Now, in reality, there's no meter sticks that are massless. But let's start off easy, and let's say it's massless. If it's massless, then it would just be those two forces, right? Okay. So right here at the 60, there would be a force upward that's that long, and that long as well. So the support force on the meter stick from the fulcrum. Yeah. And I know those forces, this support force has to be the sum of those two because is it accelerating? No, it's not accelerating. If I'm looking at this picture, it's not accelerating upward or downward, left or right, or any other direction. It's not accelerating. So by the first condition of equilibrium, the acceleration is 0, so the net force has to be 0. Okay. So you've got that picture now in your free body. What I want you to do in number 3, the second part of number 3, go ahead and read that. I'd like you to go ahead and write an equation and solve it. So if we can stop what we're doing and kind of look at the group that's presenting up there. So they've got all the free bodies and they've got the extended free body. The extended free body is really important whenever something could possibly rotate, which the meter stick could. And so we see all the forces acting on the meter stick. And so they found the support force is equal to the sum of those other two forces. So 1.2 plus 2, and they get 3.2 newtons. Any questions? Okay, while they're still up there, number 4, it says, what is the acceleration of the meter stick? It's 0. Okay. And this is a little bit tougher. So number 5, it says, how would your answers that you've already answered, and they're all there, it's nice, how would they change if the fulcrum would move over to, let's say, the 50? So let's start with one thing, because it's kind of a trick question. Let's go slow on it. Does the free body diagram for the 120 gram mass change? Would the 200 grams mass free body change? No. If I move the pivot point over, we already said that those two downward forces wouldn't change. Is it going to be accelerating upward, downward, left or right, or anything like that? No. So would the support force change? No, it wouldn't. Okay. So would it be in equilibrium? This is another kind of trick question. It's not accelerating anymore, but you're saying what? It has an angular acceleration, right? It's going to start rotating. So it's not in equilibrium anymore, right? If you move that fulcrum over, even though all the forces stay the same, even though it's not accelerating left or right or up or down, it's going to start rotating. So it's not in equilibrium. Any questions? Okay,
But not being in equilibrium doesn't
There's
mean...
two conditions for equilibrium. One is the acceleration is equal to 0. And this one's, even if you move the fulcrum, the acceleration is still 0. But the second condition is that the angular acceleration has to be 0 as well. And if you move the fulcrum over, it's going to start out with no angular velocity, but then when you let go of it, it's going to start.
It's going to tip.
Yep.
Okay.
So there's two.
So tipping means angular.
There's going to be, it's going to go from one angular velocity to another one, which means it's having an angular acceleration.
Got it.
Okay.
So the deceleration is talking about number 4.
Yeah, that's only, we're only talking about translational. I should have specified,
So
no.
it's going to specifically say angular.
Yeah, I should have specified. Yep. So when it says number 5, equilibrium, we're talking both translational and rotational. And so the answer is no, because it's going to start rotating. Any questions? Okay, give me a hand. Thank you. Okay, so if you can stop what you're doing, look, the group that's up here. They said 1.2 newtons times the distance away, which is 0.5 meters, times the sine of 90. And they got 0.6 newton meters. And they had to look at it to figure out which direction that would be, and they said counterclockwise. Any questions? Oh, I usually put a dot there. I don't think it really matters, though. You can go N, M. However, if you want to put the M on the other side, so it's on the precedes the N, you need the dot, because if you don't, then it looks like millinewtons. Any questions? Okay, give me a hand. Nice. could you please start working on the second part where it says determine the torque from the support force? Okay, if you could please stop what you're doing and look at the group that's up here. It says determine the torque from the support force. So they have the support force is 3.2 newtons. They have the distance away is 0 meters and sine of 90, and they get 0 newton meters. Any questions? So this is the same thing as if I tried to open the door by pushing where?
At the straight up, like on the,
On the floor of the door.
Yeah, show me. I like this. Yeah, show me.
okay.
What do you guys think? Is that what it's like?
No, am I wrong? Okay, I.
No, wait a second. Is it?
I mean,
No, it should be. It is too.
yes.
Yeah,
Oh, it would be if
I
they
think
did
that's right,
that.
isn't it?
No.
At first I didn't see it, but I think that's good. I think really, that would work. However, I think the example we have here, because of course the angle is 90, I think it would be more like pushing here, wouldn't it?
Yeah,
Because then the force would be, or the angle would be 90 degrees.
but both of them would still give you 0.
Yes, both of them give me 0. Even this one here is through the pivot point. I agree. So I
But
agree
it's
with
not
that.
at 90.
But the angle there is actually 0 degrees. So I agree that the distance is still 0, or the answer is still 0. I agree. Okay.
That's because of the which way horizontal.
Yeah, it's because I'm just going by the picture there, and it shows the angle's 90 degrees. So to get to 90 degrees, it has to be right there at the pivot point. Right. Any questions? Okay, give them a hand. Nice. Okay, I'd like you to work on the next one where it says determine the torque from the right-hand side. Okay, for this one, it says find the torque from the right-hand side, and they have a force of 2 newtons times the distance away, which is 0.3 meters, times the sine of 90 degrees, and they got 0.6 newton meters clockwise. We agree with that? Okay, give me a hand. Nice. Okay, so if you could look up here for a second, because I want to do the next one together. So I think you guys said that the clockwise, this was 0.6 newton meters counterclockwise on this side. This one here, I think you said the torque was equal to 0 newton meters. And this one here, I believe you said the torque was equal to 0.6 newton meters counterclockwise. Excuse me, clockwise. Now I need to find the net torque. Now is when I'm going to start using those positives and negatives. Okay? So I have 0.6 newton meters counterclockwise. Is that going to be positive or negative? Positive. And the reason again is because math class decided to go counterclockwise for naming their quadrants and measuring angles and stuff. Plus 0. And what about the clockwise torque?
That would be negative.
That's negative? Okay, so minus 0.6 newton meters. And so I get 0 newton meters. Which it's not accelerating, and there's no angular acceleration because the net torque is 0. So is this an equilibrium? Yeah, and we knew that already because it said it was balanced. Okay. All right, for the next one. So we're getting ready to look at number 7. Erase this here, erase that. Okay, the thing that changes in number 7 is I would like you to go ahead and draw in the forces on the picture given in number 7. So it still has the same force acting over here at the 10 centimeter mark. It's 1.2 newtons, just like the last one. And it still has the same support force acting. Where was that acting before?
60 centimeters.
At 60, so put that at the 60 centimeter mark, and that was how many newtons? 3.2 newtons, okay. And there's still tension over here on the right, and where was that acting before? At 90, so it's acting at the 90 again. How big was that one?
2 newtons.
2 newtons, okay. So those forces are still there at the same point, at the same size. The thing that's changing is I'm going to choose to put the pivot over here. Okay, so once you've got those forces drawn, could you look up here? Because this is where it gets a little confusing. I want to make sure everybody's on track here with this. Okay, so this was the original setup, and we already know it's balanced. It says that it's balanced. In the very first sentence, it says it's balanced. Okay? So if it's balanced, where is it pivoting about? Or is it pivoting if it's balanced?
No,
It's not pivoting, right? So the truth is, even though that's the fulcrum, the pivot point could be anywhere since it's not pivoting. It's not pivoting, so the pivot point could be anywhere. It's not rotating. That doesn't mean, stop what you're doing, look up here. That doesn't mean I'm going to say, okay, in this problem, I'm moving this, the fulcrum over here. No, the fulcrum is not moving over there. The fulcrum stays there, right where the support force is. I'm just imagining that since it's not really pivoting, that I'm going to put the pivot point over here. Does that make sense? So the fulcrum's still here, the tensions are still there, it's not rotating, so I'm just going to imagine that it's rotating there, or might rotate there, I don't know.
If it were to, it would be
If
over
it
there.
were to rotate, that's right. Okay? So what I would like you to do is, what it says in number 7, is I would like you to find the torque from the left side, the torque from the support, and the torque from the right side. Okay? Since you have at least 3 people in your group, you could have each person grab a marker and have them do the different torques. Don't forget to also put down clockwise and counterclockwise, depending upon the direction. I think a lot of people are doing okay. Let's forget about the directions for right now. What do you guys get for the torque over here on the left? I don't want direction, I just want your magnitude, the amount.
0.096
0.096 newton meters?
Yeah.
Everybody agree?
Yeah.
So 0.096 newton meters. What about the torque from the support? What do you get? 1.856?
Yeah.
Okay. Please say something if that's not what you're getting, newton meters. What about the torque from the right-hand side? What do you get?
1.76.
1.76 newton meters? Everybody agree? Okay, I want to talk just briefly about direction because sometimes that's confusing for students. So let's talk about the one over here. We'll do all the directions, but we'll start with just the one on the right-hand side. Imagine, immediately looking up here, imagine that we're looking at a door from above, and here's the hinge over here where the pivot point is. Ignore this force or erase it, so it's not there. Erase that force. So we're only looking at one force there. Is that going to make the door rotate down or up, that force?
Down.
Down. So which direction is that then?
Clockwise.
That's clockwise. Okay, now imagine that those 2 forces are gone and we only have that force on the door. Which way is it going to rotate? Upward, right? So that would be counterclockwise. And now, this is probably the harder one. Get rid of those 2 forces, and now we're really close to the hinge. We're not on the hinge, though. And we have this force that's down. Is it going to rotate?
Yeah.
And which way? Is it going to be up or down?
Up.
I hear some people saying up, I hear some people saying down.
I don't know.
So here's the hinge, and here's the force.
Oh wait, are you talking about the one that's closest to the point? Oh, I was looking at the one that, well, I was looking at the other one. It's going down.
Okay, everybody looking up here. Right here is our hinge, right here. And we have a force attached here pulling this way. Which way is it going?
Down.
Down. So is that clockwise or counterclockwise?
Clockwise.
Clockwise. Okay, now let's find the net torque. This is where we're going to use positive and negatives. Will this be positive or negative? Negative. Negative 0.096 newton meters. This one here will be what? Positive or negative? Positive. We have to continue this tomorrow. Please keep on working on worksheet 1. I'll try to get my